Hello, everyone. Good morning, good
It's
afternoon,
nine
and
o'clock.
good evening, everyone, wherever you are joining from. I'm Abhijeet, and I have spent over a decade working at the intersection of software, data, and intelligence into AI, building a large-scale systems, machine learning pipelines, and real-time decision engines across adtech, fintech, healthcare, and semiconductor. I have worked on just about everything from high performance Python system and AI driven automation to cloud scale data engineering. So I have seen the full life cycle of the idea from like a Jupyter notebook that barely runs to distributed system that handles billions of requests every single day. And if there is one constant in the journey, it's been Python. So Python has been my companion, my go-to for experimentation, my comfort zone. But I'll be honest, it's all also been my bottleneck. So I have seen brilliant ideas slow down, not because of the logic was wrong, but because Python simply couldn't move fast enough for a production workloads. And every time we end up doing the same dance. Prototype in Python, rewrite in C++ or Rust, maintain both forever, and pray the behave the same. That pain, that that pain between the flexible and performance is exactly what today's talk is about. Because now there is a new language that promises the bridge that gap, a language that feels like a Python, runs like a C++, and scales like a compiled system. Ladies and gentlemen, let's welcome to a Mojo talk. Let's start with something we all know. Python runs the world of computation today. From automation to AI, from dashboards to data pipelines, is the duct tape of modern computing. But duct tape has its limit, especially when you are trying to build a rocket ship. Python's superpower is simplicity. It's expressive, it's human readable, and it's forgiving. But under the hood, it's struggle with a performance, interpreter overhead, dynamic typing, and of course, the global interpreter lock. Now, Python 3.14 has introduced no-GL runtime, which is a big step forward, but even then, we can't escape the interpreter speed limit. It's still like asking a marathon runner to sprint in the flip-flops. That's the motivation behind Mojo, a language that asks, what if we could keep everything great about Python and make it blazing fast? Mojo mission is simple yet powerful, one language for both research and production. No more rewrites, no more dual ecosystems, just pure efficient computation with Python souls intact. You know this pattern. You start in Python, exploring, testing, iterating. Then, when things get serious, you rewrite the core in C++ or CUDA. Now you are maintaining two code bases, and somehow they both work, except or alternative Tuesdays. You fix one, the one breaks. You debug one, and the bug politely moves next door. It's like playing whack and mole with your code. We all have been there over the years. We have tried everything Python, Numba, Jax, Pipey, Rust, Rust bindings, all brilliant efforts, but they only solve part of the problem. None truly unify Python's elegance with compiled speed. Mojo changes that. It's not Python with extension, it's a compiled language with Python compatibility built right in and secret weapon MLIR, a multi-level intermediate representation. This Think of MLIR as a translator that doesn't just understand your code, it understands your intent. It looks at your loops, your tensors, your memory layouts, and says, okay, I know what you mean. Let's make that really fast. So instead of wrapping Python in faster parts, Mojo turns your Python code itself into the fast part. So Mojo was created by Chris Latner, the same mind behind LLVM and Swift. When the guy who built LLVM says he's working on a new language, you know something serious is coming. The goal is clear: performance, safety, and Python compatibility. Mojo feels familiar. It looks like a Python, but it gives you a powerful new tools, optional static typing, deterministic memory management, and explicit mutability with let, var, and inout. It uses value semantics, so you have predictability without garbage collection surprises. Under the hood, the compiler follow a clear pipeline: parser, MLIR, LLVM, binary. So it can just just in time for interactive work or AOT for full production binaries. And the magic is MLIR, it can optimize your code for a tensor loops and data flow all the way down in the hardware. It's like having a compiler that doesn't just run your code, it's understand your code purpose. All right. So let's look at something practical: how Mojo and Python compare in real code. So what you are seeing here are two versions of the same program. On the left, we have a Mojo. On the right, we have Python 3.14. Both are calculating the sum of squares, same logic, same flow, same structure. If you notice, they look almost identical. Both have loop, both have like use of variables, both return a result. Even the indentation feels like a home for Python developers. But one of them, the Mojo version, is quietly packaging a jet engine under the hood. So let's take a closer look. Mojo declares its variables with explicit types like int 128 here, which gives the compiler enough information to fully optimize the loop. Python, meanwhile, uses a dynamic typing and runs this logic inside the interpreter. In practice, that means Python is thinking about each operation as it runs, while Mojo already knows exactly what to do, and it's off to the races. Now, let's make this real. Imagine loop updating hundred of millions numbers. Python Python smiles and says, "Sure, I'll interpret each one carefully." Meanwhile, your CPU quietly cries for help. Mojo, on the other hand, runs the same loop, identical syntax, but compiles straight to vectorized machine code. The result? It runs hundreds of times faster. Python says, hold on, I'm thinking. Mojo says, done, next problem. That's the difference. No new syntax, just a new speed. So now let's see what happens when we actually run both versions. So here is a comparison we have. So this test ran on the same machine with both loops computing the same thing. Now look at this first line. Real-time Python took about like 0.68 seconds. Mojo finished in like 0.31 seconds. That's roughly like 2.2 times faster. End up end to end. And remember, like this isn't even GPU or parallel work. This is just like a plain CPU code compiled efficiently. If you glance down, at instructions retired, you will see Python executed almost 150 times more instructions that that's the interpreter overhead. Every operation going through layers of runtime management. Mojo doesn't have that problem. It compiles straight to machine code and runs those loops directly on the CPU. Then look at CPU cycles. Python burned about like 74 times more cycles. It's like watching someone pedal a bicycle uphill while Mojo glides by an electric car. So, what does this tell us? Same syntax, same logic, but Mojo executes fewer instructions, fewer CPU cycles, and still gives you the same result, just much faster. It's the difference between interpreted and compiled. Python reads your code as it runs. Mojo understands it before it runs and optimizes it down to the silicon. It's like having a Python friendliness powered by C++ HUD. So yes, both scripts look eventually readable, but when you hit run, Mojo gets a job done while Python still stretching its legs. That's the first test of what Mojo's compiler magic really means. Now here, the best part. You don't have to be abandon Python to use Mojo. You can literally write Python import NumPy, Torch, PyTorch, and your existing libraries will just work. You can just run Mojo standalone, call it from Python, or soon simply import Mojo modules directly with import like my Mojo. So this means you can deep orchestrating your pipelines in Python and move only performance critical sections into Mojo. Think of like upgrading your car engine, not buying a new one. In scientific enterprise environments, reproducibility is everything. Mojo already integrates smoothly with Pip, Conda, Mamba, and Pixie, and it fits perfectly in container systems like Docker, Podman. The future roadmap includes deterministic log files, GPU and TPU specific wheels, and multi architecture packaging for consistent builds everywhere. So you so your code runs identically from your laptop to the cloud. And yes, that means you can finally retire the phrase, it worked on my machine. Okay, so this is where Mojo really shines. It's being used in HPC kernels, tensor math, pre-processing, and interference workloads. Basically, all the places where Python usually starts sweating. Mojo, powered by MLIR, directly targets CPU and GPU and TPUs. It automatically vectorizes, parallelizes, and optimizes a compute heavy tasks. It integrates with a modular engine, Onyx runtime, and VLLM, and new frameworks like Mojo Torch and Mojo ML are already taking shape. We are witnessing the beginning of new performance ecosystem, one where Python level productivity meets HPC level speed. No great language succeeds without a great tool, and Mojo comes prepared. You get the full SDK with compiler, REPL, and static analyzer. There is a Visual Studio Code extension for syntax highlighting and IntelliSense, and yes, a Jupyter kernel for interactive experiments. The modular hub is a Mojo's own PyP, a package repository for Mojo's modules. And for production, Mojo integrates seamlessly with CI/CD, GitHub Actions, Docker, and container registries. So whether you are prototyping or deploying, Mojo fits right in. Now let's keep it real. Mojo Mojo is not perfect. Its standard library is small. Windows support is in progress, and part of the compiler are still like closed source for now. Also, Mojo introduces a new concept like value semantics, explicit mutability. So for a long time, Python devs, it's small mindset shift. But once you adapt, the control you gain feels worth it. And yes, the community is small, but remember, Python was once small too. Everything big starts small, and Mojo's trajectory is it's steep. Looking ahead for future for Mojo, Mojo is a bright. We'll see full standard library coverage, GPU and TPU compiler backends, and complete open source under the MLIR and LLVM ecosystem. But Mojo isn't trying to replace Python, it's trying to complete it. Python remains the brain, the conductor, Mojo becomes the muscle, the performer. Together, they form a unified ecosystem, while your research prototype and production system finally speak the same language. Imagine writing your code once and running it anywhere, from laptop to a supercomputer with C++ level performance. So, to wrap up, Mojo merges Python's readability with compiled performance. It solves the two language problem, unifies research and deployment, and it gives developers the freedom to build fast without leaving Python's ecosystem. You don't have to change how you think, just how your code performs. Mojo isn't Mojo isn't end of a Python journey. It's the next chapter. Mojo isn't about like a replacing Python. It's about extending it. It gives Python's ease of use, but adds a production level performance and reproducibility. A chapter where reproducibility meets a raw power and research meets a real production. For AI, and scientific computing, that means faster experience, fewer rewrites, and smoother path from research to production. If you are curious, I encourage you to try Mojo Playground and experiment with small ML or scientific workloads. Or as I like to say, Mojo for when your Python needs caffeine, but you don't. Thank you so much for listening. You can find out this PPTs on this link, and you can follow me, connect me with the LinkedIn. You can just scan this one.